Hello, my name is Lauren Wilson, and this is Lab 3, the magnetic field of a bar magnet. In this lab, we explore the correlation between basic magnetic field and the observable distance on and off the axis from the source of the magnetic field. The applied principles that we're using for this lab were the Biot-Savart law shown on screen, as well as making sure that the magnetic dipole was modeled by a bar magnet. Additionally, we used the distance dependence formula for a bar magnet shown below. Here are the results of the lab, the magnetic dipole moment, and the magnetic field proportional to distance, shown on screen. Some procedure and assumptions for the lab. Starting the procedure, we had to determine the direction of magnetic north, and we lied a phone flat on a table, rotated until x component equals 0 using a magnetometer app. We set up meter stick orthogonal to north and define the magnetometer location that's inside the phone. So we slide the phone perpendicular to the meter stick in x and y direction and mark axes with edges of tape. And then from there, we move the phone into various distances along the meter stick, taking measurements on the app and from the distance using the ruler. The systems and surroundings, the system is the bar magnet and phone, and the surroundings is everything else. Assumptions for this lab. For the model, we assume that the bar magnet acts as a magnetic dipole. Experimental data for the on-axis. The values were found using a ruler and just the distance and magnetic field shown on the magnetometer app. And the values found were linearized by taking the natural log of each side and then graphed. So the natural log of the x component for the magnetic field versus the natural log of r. And you can see the equation we used below. Calculations. We used the equation from this graph based on the linear regression. So n, its slope is negative 3.04, which is very close to our expected value, which is supposed to be negative 3. And shown on screen is the calculation to find mu. And as you see, I got 2.28. The experimental data for the off-axis part of this experiment, we positioned the magnetometer of the phone a distance d perpendicular in the x and y direction, then measure the magnetic field using the magnetometer app, and correct the y component by subtracting the magnitude of the Earth's magnetic field. And the average perpendicular distance in this case was 0.173 meters. And as you can see on screen as well, the average magnitude of the magnetic field was 1.736 to the negative times 10 to the negative fourth Teslas. This is my glow script model. I created a magnet at the origin with a magnetic moment found based off of the calculation I made in my experiment. And I made 6 arrows to represent magnetic fields, 2 arrows to represent magnetic fields on axis from the magnet, and 2 arrows to represent magnetic fields perpendicular to the axis. And this is all based off of observational points, either on axis or perpendicular to the axis. Additionally, I included a arrow to represent the magnetic field 45 degrees from the axis. And this is the visualization of the computational model. As you can see, the magnetic field vectors shown as well as the visualization. Some questions to consider for this lab. What if I hadn't oriented my experiment to compensate for magnetic north, but had instead laid out my meter stick at some intermediate angle with respect to Earth's magnetic field? How would my results have changed? All of the magnetometer readings would have been skewed in the direction of magnetic north. And so therefore the values of K, mu, and N wouldn't be as accurate as they are in the lab because I did compensate for magnetic north. Second question, what if I were to stick two identical magnets together end to end and run the experiment again? How would I expect my measurements to differ? So the direction of the magnetic field would be the same, and assuming that the length of the magnet is minimal, the magnitude of the magnetic field would be approximately double in value. All right, that's all I have for you today. I'll see you in lab 4.